Everybody, my name is Marshall Barker and welcome to your tutorial for today. As you can see from my last video, I have a new setup as I've moved to residence in Kingston. Nonetheless, this video is going to be filled with Chem 112 content as we discuss the topic of non-biological buffer systems, and I will be posting my email and lab number, so if you have any questions after the tutorial, please feel free to reach out. And we will now jump into the topic. Before we begin, it's important to review what we already have learned from Chem 112. The three topics are what is a buffer and what does non-biological mean. The second topic is examples of common buffers, and the third topic is the Henderson-Hulchbulch equation. So, a buffer solution contains appreciable amounts of both a weak acid represented as HA and its conjugate base represented as A-. A buffer could also be a weak base represented as B and its conjugate acid represented as BH+. Buffers can neutralize small quantities of either a strong acid or a strong base. Non-biological means not derived from biology or living organisms. However, for Chem 112, non-biological simply means anything other than the buffer system for blood. Buffers maintain the pH at a particular value. A pH less than 7 is referred to as an acidic buffer, while those which maintain the pH at values greater than 7 referred to as base buffers. Examples of acidic buffers include CH3COOH/CH3CO2- and HClO2/ClO2-. An example of a base buffer is NH4+/NH3. Furthermore, in 1908, Lawrence Joseph Henderson formulated an equation which described carbonic acid as a natural buffer. Carl Albert Hulchbulch later reformulated Henderson's work logarithmically to create the Henderson-Hulchbulch equation, a formula that measures pH derivation in terms of acidity. The equation is the middle image on this slide, and we will get into this equation more down the road. But now we will discuss the two examples of non-biological buffers. My first example of a non-biological buffer is Alka-Seltzers. Alka-Seltzers are antacids used to relieve acid indigestion and heartburn. Alka-Seltzers contain sodium hydrogen carbonate and citric acid. When this tablet is added to water, citric acid reacts with sodium hydrogen carbonate to give sodium citrate in solution and releases carbon dioxide. Sodium citrate acts as the antacid as it neutralizes excess acid by forming citric acid. The excess sodium hydrogen carbonate from the Alka-Seltzer also acts as an acid because it liberates carbon dioxide. It also neutralizes the base to help the solution resist pH change. Overall, the importance of this buffer system is to how it helps stop indigestion and heartburn. My second example is buffers in shampoo. The usage of buffers in shampoo is to regulate the pH levels to prevent one's scalp from burning and keep one's hair clean and healthy. The shampoo is kept slightly acidic because the alkalinity of the soaps used can damage one's hair. The ideal pH range for shampoo is between 5 and 7. When citric acid and sodium hydroxide are added to water, they create sodium citrate, which is a common buffer to maintain a slightly acidic pH. Overall, this non-biological buffer system is vital to keep one's hair clean and healthy and prevent the scalp from burning. Now that we've done some review and we've gone over two examples of non-biological buffer systems, we will now jump into some practice questions. The first practice question is, what is the pH of a buffer solution that contains 0.05 grams per mole of sodium acetate and 0.1 gram per mole of acetic acid? Note that Ka is equal to 1.76 times 10 to the negative 5 with a pKa of 4.75. Now please pause the video and try this question on your own. I hope everyone paused the video to give this question a try, as this will be on your tutorial assignment. But now I will explain how I got my answer of a pH of 4.45. So the first thing you want to do is write your equation and then fill in your ice table. After your ice table, you want to create a Ka expression with products as the numerator and reactants as the denominator. After you fill in your Ka expression with the values from your ice table, and you should get 0.05 plus x times x divided by 0.1 minus x, but because these numbers are small, x is negligible, so the answer actually changes to 0.05 times x divided by 0.1 to make it easier to find your answer. Then you fill in your Ka value from the question because it's given, and when you rearrange, you get x, which is equal to the hydronium ion, and it gives you 3.52 times 10 to the negative 5. And then with your pH equation, you do the negative log of the hydronium ion, which gives you your answer of pH equals 4.45. Awesome job with the first question, everyone. Now let's move into the second question. The question reads, Head & Shoulders released a new shampoo that they claim is #1 on the market. What is the pH of the Head & Shoulders buffer solution that is 0.24 grams per mole of C6H8O7 and 0.20 grams per mole of NaOH? Does this pH fall within the normal range for shampoo, and if not, what would this pH do to your hair and scalp? Note that the Ka value is 5.6 times 10 to the negative 10, and now please pause the video to try this question on your own. Hopefully everyone's gotten the idea that it's important to pause so you can learn and prepare for your tutorial assignment, and now I'll just explain my answer. So when you have a Ka value of 5.6 times 10 to the negative 10, you want to change it to get your pKa value, so you would do the negative log of 5.6 times 10 to the negative 10, which gives you a pKa of 9.25, and then you do your pH equation, so pH equals pKa plus log of a minus divided by HA, which is the Henderson-Hultz equation. And when you fill in your values, you get a pH equals 9.25 plus log of 0.24 divided by 0.20, and you get a pH of 9.33. And this new shampoo does not fall within the normal pH range of 5 to 7, and because it is alkalinic, it may increase the negative electrical charge of your hair fiber surface, causing damage to your scalp. Awesome job with the second question. Now let's move on to the third and final question. The question reads, how would you prepare a 2.5 gram per mole buffer with a pH of 9 with triethylamine with a pKb of 6.2 and HCl? Remember to pause the video and try this question on your own. So now I'll explain my answer for the third and final practice question of our tutorial today. So you first want to start off by finding the pKa values. So you do pKa plus pKb, which is equal to 14, and the pKb of 6.2 was given in our question. So when you do 14 minus 6.2 for the pKa, you get 7.8. And then in the Henderson-Hultz equation, you do 9, which is equal to 7.8, plus a log of conjugate base initial divided by conjugate acid initial, and then you get log x is equal to 1.2, and then when you're just simply looking for x, you get 10 to the power of 1.2, which is equal to 15.84893. And then next you move on to BH plus B, which is equal to 2.5 grams per mole, because you're trying to find how to prepare a 2.5 gram per mole buffer. And then you do B divided by 15.84893 plus B to give you your 2.5 gram per mole. And then B is equal to 2.35 gram per mole. And then the BH plus is equal to Cl, so HCl. So HCl equals 2.5 minus 2.35. So in the 2.5 buffer solution, HCl is only 0.15 gram per mole, and triethylamine is 2.35 grams per mole. Before I put you into your breakout rooms, let's just do a quick overview of what we've learned, and at the end I also have some fun acid-base chemistry facts. So, a buffer solution contains appreciable amounts of both a weak acid represented as HA and its conjugate base represented as A-, or a buffer could also be a weak base represented as B and its conjugate acid represented as BH+. Buffers can neutralize small quantities of either a strong acid or a strong base. Furthermore, we learned the definition of non-biological means not derived from biology or living organisms, but for Chem 112, we stuck to a simple definition that means anything other than the buffer system for blood. We also learned about Alka-Seltzers and shampoo as non-biological buffers, and how buffers maintain the pH at a particular value. A pH less than 7 is referred to as an acidic buffer, while those which maintain the pH at values greater than 7 referred to as base buffers. We also learned in 1908, Lawrence Joseph Henderson formulated an equation which described carbonic acid as a natural buffer, and then Carl Albert Hultz later reformulated Henderson's work logarithmically to create the Henderson-Hultz equation. And here are some fun, interesting acid-base facts. So both acids and bases conduct electricity because they separate into ions in water. Any aqueous liquid classifies as an acid, base, or neutral, but oils and other non-aqueous liquids are neither acids or bases. Also, a common test of whether an unknown is an acid or a base is to wet litmus paper and test the substance. I will now show you my references if you want to do additional research for one of your quarterly quizzes. So that's it from me. I really hope you enjoyed this presentation and you learned a lot of information about non-biological buffer systems. And remember, my email is 19mjb18@queensu.ca. And if you have any questions, feel free to email me. And now I'll put you into your breakout rooms to complete your assignment.